All right, so our discussion for today has to do with Gaussian optics. We've touched on Gaussian optics in the past, whether you realized it or not, and that was when we were talking about effectivity. And so in terms of effectivity, we were talking about an eye, that eye had some sort of refractive error, and we were going to compensate for that refractive error by putting either a contact lens on the surface of the eye, or we were going to put correction out into space some here, and we call those spectacle lenses. All right, you'll notice that although this system and this system, either the contact lens system or the spectacle lens system, is designed to compensate for the refractive error, because these things are in two different positions in space, we call that the vertex distance. In this case, I'm using the little h for that. The powers of the spectacles and the contact lenses to create the same equivalent power, i.e. emmetropia, is going to be different. All right, and we needed to come up with some sort of way to do that. One of the ways was to talk about the focal distance of the contact lens as juxtaposed to the focal distance of the specs, and turn that back into a dioptric power, and then coming up with the answers. The cheat was using the Gaussian formula. And in the Gaussian system, what we're doing is we're saying that this equivalent system, which could be the spectacle system or the contact lens system, had to do something with the powers of the lenses involved. All right, so the equivalent system for the spectacles was going to be the power of the spectacles would be involved, the power of the eye would also be involved, and then because of this distance in between the two, there had to be some sort of compensation factor, and that compensation factor is the vertex distance. Also involved is the power of the specs, and then times the power of the eye. All right, and you'll notice that this is the normal Gaussian form that you'll see again and again. We can also do the same thing for the other system, which is the contact lenses. In this case, it's going to be the contact lens plus the power of the eye itself, minus that vertex distance, although the vertex distance would be 0 with a contact lens. We're still going to write it in to show where it comes from, times the power of the contact lens times the power of the eye. All right. Now we have two formulas here, but both of these formulas, the D equivalent for the spectacles and the D equivalent for the contact lenses, are going to be the same. In other words, we want to take this eye with a refractive error and make it into a quasi-emmetrope. And so simply all we do is just now equate these two. So I'm going to take the D specs plus the DI minus the vertex distance times the power of the specs times the power of the eye, and make that equal to the power of the contact lens plus the power of the eye minus the vertex distance times the power of the contact lens times the power of the eye. So we're left with this very long and ugly looking equation here, but we can simplify this down relatively easy. All right, now on this side we're dealing with the equivalent power of the contact lenses, and so the vertex distance of a contact lens is going to be 0. In other words, we're assuming that it's on the surface of the eye. Therefore, everything after 0 times this times 0 times this. So this entire portion of the equation now disappears. All right? How else can we simplify this down? Well, the power of the eye is the power of the eye with the contacts, and the power of the eye is the power of the eye with the specs. So in other words, those are equated to each other. They're the same, and they're on opposite sides of the equal sign, so we just eliminate these two. We can cancel these two out, and you notice that we're left with 1, 2, 3 different powers, and here's the power of the eye on there. So what we'll have is, let's say, the power of the specs, and we can simplify this down with a little algebraic magic, which would be the power of the contact lens, the D power of the contact lens over 1 minus, in this case it's going to be the vertex distance times the power of the contact lens itself. You could also do it the opposite way. If it works one way, I can also simplify it the opposite way, and then the power of the contact lens is going to be equal to the power of the specs, 1 minus the vertex distance times the power of the specs itself. Okay, and either way you can work back and forth between the two. All right. The only rub in this case is, once again, knowing the sign of the vertex, and that had to do with our normal sign convention. In other words, with the path of light is going to be in a positive sense, okay, and against the path of light is going to be in a negative sense, assuming that way light travels from left to right when we draw our pictures. And so you know this as the effectivity formula or the vertex formula. formula, okay? Whatever words you want to use, all right? And so now we're going to take this very narrow topic that we applied that to and apply it to something called a meniscus lens. A meniscus lens is the shape of all dress ophthalmic lenses, okay? Once again, I have light going in this direction, which means my front curvature is a positive base curve and my back base curvature is always a negative. It doesn't matter whether or not the overall power of the lens is positive or negative. The front base curvature is positive and the back base curvature is negative. And we also now have some sort of thickness of the lens itself. In the same manner, you can't ignore the vertex distance. We can no longer ignore the thickness of the lens itself. We have to account for it. All right? And so we can apply that same Gaussian formula to what we're dealing with here. And so this system has an equivalent power. The equivalent power, in this case, we're dealing with the eye and the contacts, or the eye and the specs, but over here we're dealing with the back and the front powers. And so this equivalent power of this system here is going to be a combination of the power of the back surface plus the power of the front surface minus our compensation factor. In this case, we're going to use a T because we're talking about the thickness of the lens, all right, times the power of the back surface times the power of the front surface. And we have something very similar to what we had before because we're using the same concepts. All right. Now, in this case, we're talking about a lens, and that lens has a positive front base curvature in the case I drew it, and a negative back base curvature. All right, and I'm going to put an eye over here somewhere. All right, so generally the light we're going to have traveling in this direction, this way. All right, now I can read the power of this system. Here's our thickness over here. I can read the power of this lens in one of two ways. I can put it into the phosiometer, or the lensometer, the way you guys call it, in such a way that the back of the lens is up against your machine, or I can also spin it around and place it so that the front of the lens is actually facing into the machine. All right, in the normal way, the light is actually coming from the front to the back. If you flip the lens around, the light is then coming from the back to the front. All right, and in this case, when we're having the light coming in normally, in other words, the positive curvature is facing away from the patient, the negative curvature is facing towards the patient. When we read the power in that aspect, we call that back vertex power. Okay, so the power is read from the back end. We can also flip the lens around, and then we call that the front vertex power. Okay, so the lens can be used either way. If you notice in this case, when you're dealing with back vertex power, the light is actually entering the front of the lens first. When you're reading front vertex power, the light is actually entering the back of the lens first. Okay, and so we're going to simplify this formula down the same way that we did over here. And what you have is something that is called the front vertex power. That front vertex power is going to be a combination of the equivalent power that you determined here. 1 minus, in this case, it's now going to be the thickness of the lens, and because we're dealing with front vertex power, the light is hitting the back of the lens first, and so that is what's going to drive this one. We can also determine what the back vertex power of a lens is. That's going to be determined by the overall equivalent power, 1 minus. We have to compensate for the thickness, and in this case, the back vertex power, the light is actually hitting the front lens first. So this is the power of the front. Okay, and so this gives you your basic Gaussian equivalent power, your front vertex power, and your back vertex power. And you'll notice that the form of all this is very similar to how we derived our effectivity formula, because it's all coming from the same basis, all right, from the same idea. All right, so there's no reason for you to memorize stuff again and again. Just understand how these things are derived, or what concepts that they come from, and you can always work your way backwards. All right, so now what we're going to have in reality is some sort of lens. The lens in this case we're dealing with has a positive front, and it has a negative back, and it has some sort of thickness between the two. All right, where that is in line, that's going to have some space. So this is actually the physical measurements. In other words, this actually is in reality. Okay, this is how you're going to actually determine the measurements in reality. I know it has a front surface, I know it has a back surface, and then it has some thickness in between the two. All right. Now I'm also going to have some sort of focal point of my front vertex power, okay, which is going to be out in space over here somewhere, all right? And so the front vertex power reading is going to be over here. So power of the front vertex is also going to have some focal point of the front vertex. The back vertex power, which is going to be on this side, the back vertex power is also going to have some associated back vertex power focal point is going to be in there. All right, and the way I go from here to here is nothing more than take the inverse of that power. Okay, so simple enough. All right, now once again, we're not dealing inside the lens. We have some sort of glass or plastic, but either in front of the lens or behind the lens, we're assuming that we have air. Unless you're dealing with a patient that's in a swimming pool, we're not going to say that. We're just going to say it's in air. Therefore, our numerators in both cases are going to be 1. So if you want to know what the focal point of the front vertex power, the front vertex power and the back vertex power, just take the inverses of their associated dioptric powers. Right? Now, you're also going to have something called where the power of the equivalent power is going to be. And that equivalent power is going to have its own front and its own back. And those are the things that we're talking about, the H-planes. And so the front power surface of the Gaussian system or the equivalent system, we're going to call that the H-plane. And in that case, I'm going to call it the H1. You can call it whatever you want. And it's also going to have the equivalent power of some sort of back surface. Okay, and that's all. And that is going to be the H2 plane, the way I'm calling it. All right. And so I'm going to have focal points for each one of these values. I can take the focal point of this, take the inverse, take the inverse. I can take the inverse of the front and the back vertex power, all right? And then these equivalent systems are also going to have their own focal point. I would just take its inverse. And then the difference between the two, we're going to call that E. And so for the front, I'm going to call it E, and for the back, I'm going to call it E prime. So the physical distances between the two. And then you can also calculate those for yourself. Easy enough. So in this case, these two lenses here, this surface and this surface actually exists. Okay, this surface and this surface only exist in our Gaussian world. Okay, and so what happens is, the reason we wanted to do that, why we wanted to create that, is that we wanted some system that worked the same way as we did in the old days when we assumed that lenses had no thickness. All right, so if I had some sort of lens over here, this was an SSRS, all right, it had no thickness. I had some sort of object over here, and when I wanted to do a ray trace diagram. In other words, I ran my nodal ray through here. All right, I had some sort of parallel light that entered the system, and that parallel light, this is a plus lens, so it converged, and it converged through the focal point. I had a focal point here, and I had a focal point here, and then that light converged over here, and then that gave me my nice, cute little real image, right? So real object, okay, object is in object space. This gave me an image, a real image. The image is in image space. And that's what we want to get back to in the case, something that has no thickness. So when we're dealing with our Gaussian system, we're going to mimic the way we used to do it when we used to live in Disney World. All right, so I'm going to put my real object over here. This is in front in object space, okay? And I'm going to draw through my nodal ray. Now my nodal ray is going to go where the lens intersects the optical axis, okay? But once again, this system, this equivalent system, has no thickness. Therefore, nothing happens inside here. This doesn't exist. This is some sort of rift in the time-space continuum. So as the light comes through here, it just comes out over here. And then once again, I'm going to have that parallel light entering the system, okay? It just goes boom from here to here. Nothing happens inside. And then once again, if we're saying that this is a plus lens, then this is also going to be a plus lens. And then what I have is a converging ray here, and then I have my real image that's formed over here. All right, so when you're doing your ray trace diagrams, from your H1 and your H2 planes, or the front surface of your Gaussian equivalent, or the back surface of your Gaussian equivalent, however you want to describe them. All right, nothing happens inside. So wherever it enters the H1 plane, it leaves the H2 plane at exactly the same space. Right? And so that's how you equate one to the other if you needed to do a ray trace diagram. All right. I think most of the problems we're going to do today, we're just going to do mathematically, so we'll work our way through. But if you're required to do a ray trace diagram, that's how it would look for a Gaussian system, and that's also why it works for the Gaussian system, because that is what we want to do. We want to take a complex system and turn it back into the way we looked at it in Disney World, where everything was in SSRS. All right, so next one we're going to have two problems. One's going to be a meniscus lens and one's going to be a biconvex lens, and we'll work through those problems in a bit. Okay, so we're back for doing some problems, and here's the problem set that you have. Two problems. In the first case, we're dealing with a meniscus lens, positive front base curvature, negative back base curvature. In the second problem, we're dealing with a lens that has the same overall power as you would wear them as glasses. In other words, the back vertex power would be the same. But in this case, it has both a positive front base curvature and a positive back base curvature. Although you'll notice when we do the work that these two lenses are going to perform differently, although they have the same back vertex power. All right? So we'll get started on this. In the first problem, this is the meniscus lens that we're dealing with here. You're told in the problem, so obviously it's a meniscus lens. It has a positive front base curvature and it has a negative back base curvature. That front curvature is given to you as a +6. The back curvature is given to you as a -2. You're told that the thickness of the lens is 10 centimeters from here to here, so from the front surface to the back surface. And you're told that the lens is made out of a material that is 1.5. Okay? All right, now the problem wants you to find the system powers. Okay, and those system powers are basically going to be the equivalent power, the front vertex power, and the back vertex power. All right, so to find the equivalent power, all right, in this case it's going to be the power of the front surface of the lens plus the power of the back surface of the lens minus our compensation factor, which in this case is going to be our thickness, okay, times the front surface power times the back surface power. All right, putting numbers into this, the front surface power is given to you as +6. The back surface power is given to you as a -2. Now the thickness here, we need to be a little careful when we were dealing with specs and contacts. All right, so I had a contact lens here, I had a spectacle lens here. The stuff that was between the two was air, okay? There was nothing in between. In other words, our n was equal to 1, so we could cheat and just say that the distance, so the h was just whatever the distance was over 1. In this case, the light is actually traveling through some sort of plastic or glass with an index of 1.5. So when we do our thickness here, we actually have to put in our thickness, which is our 10 centimeters, but we need to divide it by that index of refraction itself. Okay, so don't miss that, all right, because now we're dealing with an actual lens. There's something in between. In other words, air, plastic, air, whereas when contacts and glasses, it was air, air, and air. Okay, on a contact lens, it was just your eye. All right, so don't forget to divide by your index of refraction. So the thickness of the lens divided by its associated index of refraction. All right, once again, times the power of the front of the lens times the power of the back of the lens. And when you do this math, this guy comes out to be, excuse me, a +4.8 diopter lens. All right, now in the old days, if you said this was a 6 diopter trial lens and this was a -2 trial lens, you just added the two together, and so a +6 and a -2, that would give you a power of this thing if you read it in a photometer, which would be a +4. And you'll notice that a +4 and a +4.8 ain't the same. So once again, you cannot ignore the thickness of lenses. It will not work the way it did when we were in Disney World with lenses is having no thickness. All right, so 4.8 is the equivalent power of this lens itself. I can also find the front vertex power of the lens. The front vertex power of the lens, very similar to our effectivity formula. In this case, the numerator is going to be the equivalent power, 1 minus, once again, this thickness that we're dealing with over here. Now, if this is the front vertex power, that means the light is actually entering the back of the lens first. So it's the back base curvature that I'm interested in with the front vertex power. The equivalent power you just found here, that's your plus 4.8. 1 minus your thickness, once again, is given to you as 10 centimeters. Don't forget the index of refraction is 1.5, and then this is times the back power, or the back base curvature, which is going to be a minus 2. Okay, if you work out the math for that, that guy comes out to be a plus 4.24 diopters. All right, and so once again, we're also going to find the other power, which is going to be the back vertex power. Very similar. This is going to be the equivalent power, minus 1 minus the thickness of the lens. For the back vertex power, the light enters the front of the lens first. Therefore, this is going to be the power of the front, or the front base curvature. All right, 4.8, you got that from before. 1 minus, the thickness is given to you as 10. 1.5 is the index of refraction given to you on the problem. The front power is our plus 6. Okay, and then we work out the math that way, and that gives us a power of plus 8. All right, and so what you'll notice that is that the back vertex power and the front vertex power of these lenses are completely different, and also it's not even close to what you were talking about in the old days, where you just added the front and the back together. All right, and so you get an idea of how the thickness, not only the thickness, but also the index of what the lens is made out of, is going to vastly change the performance of that lens and juxtaposition of the base curvatures of what we're dealing with. All right, now we also have to find out the focal lengths of what we're dealing with here. All right, so the focal length of the front vertex power. All right, so this is our front vertex power again. All right, now you want to find the focal length of that front vertex power. Just take its inverse. So I take the inverse of the front vertex power, and that's going to give me the focal distance of the front vertex power. I can also take the back vertex power, and if I wanted to know its focal length, it would just be its inverse, and so that would be the focal length of the back vertex power. All right, now notice in this case I also have to deal with my numerators. All right, but now when you're dealing with front and back vertex power, that is outside the lens, not inside the lens. So what we have outside the lens is air on this side and assumed to be air on this side. Okay, unless you're in a swimming pool, which you would have water and water, but it doesn't tell you that in the problem. Therefore, we'll assume air in the front and air in the back. Therefore, our numerators are nothing more than just 1. Okay, so it works out pretty well. So if I want to find the focal distance of the front vertex power, I'm going to take the inverse of what you determined what it was over here, which is the 4.24. Okay, and when you do the math on that, that's going to give you 23.6 centimeters. Okay, so 0.236, and that's going to be your front vertex power. Now, where's the front vertex power going to be? The front vertex power is going to be in front of the lens, to the left of the lens, and so that's going to have a minus sign associated with it. All right. Now you want to find the back vertex power, excuse me, the focal point of the back vertex power. You would take the inverse. Once again, we're using 1 because there's air in front and back. Take the answer that you had before, and that is going to be your 8 diopters. Take the inverse of that, and that is going to give you 0.125. All right, now that is in meters. All right, but now where is the back vertex power? The back vertex power is behind the lens, or with the path of light behind the lens. Therefore, that's going to have a positive value associated with it. All right, and so the front vertex power is going to be in front of the lens. The back vertex power is going to be behind the lens. All right, and so that gives you 2 focal distances. All right, the other thing we need to find is actually the excuse me, the focal distance of the equivalent power. And to find the focal distance of the equivalent power, that's just going to be the equivalent power, and then once again I'm going to take its inverse. Okay, and that's going to give me the focal distance of the equivalent power. Simple enough. All right, and so to find the focal distance of the equivalent power, we're going to take the equivalent power that you found, which is going to be your 4.8, and I'm going to take its inverse. Once again, we're dealing with items that are not inside the lens but outside of the lens, therefore our numerator is just a 1. I take the inverse of the 4.8, and that comes out to be 0.208, okay, and that is in meters. Now, the equivalent power is going to have, because it is now an SSRS, the equivalent system is going to be this imaginary lens. This is the power of the equivalent system. It's going to be this imaginary lens that doesn't have any thickness. So once again, it's an SSRS, which means that its primary and its secondary focal points are, you guessed it, equidistant, right? We're back in Disney World where we started out at the beginning of the year. Therefore, you're going to have a primary and a secondary focal point. One is going to be positive. The other one is going to be negative, okay? Mathematically, the values, the magnitudes are going to be the same. The only thing different is one going to be located behind and one is going to be located in front. But because the equivalent, the whole point of coming up with our Gaussian equivalent is it has no thickness, then the two focal points are going to be equidistant to each other. Same value, but a different sign. All right. Now, we want to find out where these things are located. So where our principal planes, so in other words, where our H and our H1 planes are. All right. So those are going to be the front and the back surface of our imaginary system. And to find those, it's nothing more than just the difference between our various focal points. So in this case, I'm going to say the focal point of the front vertex power, and the difference between that and the focal point of the equivalent power. And that is going to give me the position of my primary Gaussian plane or my H1 plane. And we're going to call that little funny E. Okay, and so to find that, I'm going to take the value that I had over here, my front vertex power. That was my 236, so 0.236. Okay, that had a minus sign associated with it. And I'm going to subtract from that our equivalent power for my front vertex. Once again, that is in front. So that gives me a minus 0.208, right? So minus a minus gives me a plus. Add those two fellas together, that's going to give me my E. And so the E in this case is going to turn out to be 0.028, and that's going to be have a minus sign. This number is bigger than this one, so that's going to be the value here. And so that means that my primary Gaussian plane is going to be to the left or in front of my actual lens. I can do the same thing for the back vertex power. I'm going to take the focal distance of the back vertex power minus the focal distance of the equivalent power, and that's going to be the location of my secondary Gaussian plane. I'm going to call that E prime. Once again, you can use whatever variables you want, all right, just as long as you understand what they are. All right, so the back vertex power I found over here, that was my plus 0.125 centimeters, and I'm going to subtract from that my focal point of the equivalent, which was 208, but in this case this is behind, so that's going to be plus, so I'm actually taking this one and subtracting that one from there. All right, and so when I find the answer to this, that's going to give me my E prime. My E prime, when I do this, is going to be this guy, right? So minus this. This guy is bigger than this guy, so he is also going to give me a minus value. All right, and that's going to give me a minus value of 0.083 when you do the math. All right, that's going to be the location of my secondary plane. What does this mean? That means the location of my secondary plane is actually going to be in front of the real lens. All right, so if this is my lens here, I got my 6 in the front, I got my 2 in the back. All right, whoops, excuse me, 6 in the front, and I'm going to have 2 in the back. Both of my H planes are going to be in front of this actual lens that we have. So the imaginary Gaussian planes are both going to be in front. Right? That is given by the negative value on our E prime and the negative value on our E. Okay, how is this going to look? All right, well, it's going to look something like this. I'm not going to put the numbers into it right now, but we're going to have, the reason why we're coming up with this is we wanted to get back to the old days when we had this single lens, okay, and then we had our object over here, and then we had our nodal point in between, and then we had some sort of light that came in parallel and it left convergent, and that gave us our image over here. That's what we want to have, and that is what you're going to have over here with your H and your H1 planes. And so in this case, this is going to be our lens that was given to us in the problem. There's our +6. Over here, that's going to be our -2. This is going to be my primary Gaussian plane. This is going to be my secondary Gaussian plane. Okay? And so what I'm going to have here is that this is going to be our distance between the two. That's actually our 10 centimeters going from here to here. Okay, let me just write this again because I'm running out of room. Let me do this again, and I'll do this again because I'm going to squish on top of each other here when I draw my pictures. I got 10 centimeters running from here to here. Okay, and then from our originally calculated values, I had a front vertex power that was 0.236, okay, on the other end here. And so that's going to give me our, just writing this back down again here. And so I'm going to have my E plane, which is 0.028. And so our E, this is from the other side that we talked about, our E is going to be our -0.028, excuse me. And I'm going to have my E prime, which is going to be my -0.083. Okay, and so this E value, this is from our front vertex power, so that's going to tell me where it is, where that value is going to be from the front surface of the lens, and so that's going to give me the distance between my H1 over here is going to be a distance of 0.028, so from here to here. All right, this one over here, once again, right, we're going from this is our direction of light. We're going against the path of light. That's where the minus comes into. In this case, we're talking 0.083. So here's our back of the lens. I need to go 0.083 in the minus direction, so over this way. And so this is where our H2, or our secondary Gaussian plane, is going to be. And the distance between these two are going to be 0.083. Okay, so you notice in this situation, the actual lens was here, and the Gaussian planes got shifted towards this end. Okay, and so that's basically what you're coming up with, finding your focal lengths. So we found our system powers, we found our focal lengths, and we needed to locate the principal planes and draw them on our diagram, and that's what we did there. Okay, now they're going to give you a real object, okay, and they're going to tell you that it's placed 15 centimeters from D1. That's going to be the front of the lens, and you want to know where the image location and the image size is. Okay, and then I'll redraw that picture for you in a bit, and then we'll come up with that. All right, so I'm going to redraw our pictures so we're all on the same page here, because now we're giving an object. I want to know where the image is going to be located and also the image size when it's run through this meniscus lens. All right, so the lens in reality has a 6 diopter plus front base curvature and a -2 back base curvature, and the distance between the two were given to us as 10 centimeters. Okay, we determined where our H1 and our H2 planes were. All right, the H1 plane was out in front over here. I'm going to call that H1. That's our H1. That is our primary Gaussian plane, and we found that that was, excuse me, 0.28, so 0.028 to the left. That's the distance between here and here. And we found that our secondary Gaussian plane, our H2 plane, was located also to the left of the real plane. And the distance between here and here was 0.083, and that's between here and here. All right, and so these are our real front and back and front surfaces, and these are imaginary back and front surfaces. All right, so the real system and the Gaussian system. All right, and so now we're actually going to place a real object. Real object's going to be to the left of the machine. Once again, we're assuming that light's traveling in this direction, and they're telling you that the distance between the actual front of the lens, the real lens, and the object itself is 15 centimeters. So that is from here to here, and that's going to be 15 centimeters. All right, so if it's 15 centimeters from here to here, I need to know what the distance is between here and here. So from our Gaussian front surface and our real object. And so that's going to be our 15 centimeters subtracted from this distance between the two here, which is going to be the point 028. That's an 8 over there. Can't read my own writing sometimes. So 0.028, pop my other 0 in there. And so that is going to give me 0.122. All right, so that is the distance between here and here, 122. All right, and so that is now the location of the object, real object, relative to our Gaussian system. Why do we want to do that? Well, once again, I don't want to worry about the thickness. And note that in the Gaussian system, nothing exists between these two fellas here. All right, so we can do just a standard ray trace diagram, or we can just incorporate our normal U plus D equals V. All right, U plus D equals V, right? That's the tattoo that you guys all have. And if you can't remember anything else, you can just fall back on top of that, and it makes life easier. All right, so the U coming in, that is the vergence coming in, that is the power of the system, and that is the vergence exiting the system. All right, so I want to know what the vergence is entering our primary Gaussian plane. To figure that out, I have a linear value, that's my 0.122, all right? And I need to convert that into a dioptric value, so I'm just going to take the inverse of the 0.122, and that's going to give me a value. Hold on a second, let me grab my trusty calculator here, actually my trusty cell phone. All right, that's going to be 0.122 shift inverse, and that's going to give me 8.2 diopters. Let me try that again, 0.122, and I'm going to shift inverse that, and that gives me 8.2. That's fine. So 8.2 diopters coming in. All right, now, once again, this is a real object, therefore it gives off diverging light, which means that this is a negative wavefront coming in here. So that's a minus 8.2 diopters incident upon our primary Gaussian plane. All right, the other way of looking at it is if you want to measure this position, you're measuring from here to here. That's against the path of light, and therefore this guy's got a negative value to it, and that also gives you the negative value here. All right, always more than one way to skin a cat. All right, now in this case our H1, this is our equivalent power, so now I have a minus 8.20 plus the power over here. This is our equivalent power. The equivalent power that you calculated from the past was your, let me tell you, that was our 4.8, so that was plus 4.8 diopters here, and that's going to give me my vergence coming out. All right, so I'm going to take a minus excuse me, a minus, so 8.2 minus plus a 4.8, and that's going to give me 3.4 diopters coming out the back. So a minus 3.4 diopters, right? The 8 is bigger than the 4. Right, so it gives me 3.4 coming about, which means I'm going to have a diverging wavefront leaving the back of that lens. What does that tell you? All right, that tells you I'm going to have a focal point on the opposite side. Okay, so in front of the lens. Okay, and so we're going to take that 3.4, and I'm going to take its inverse because I want to know where the image is going to be formed. So I take the inverse of the 3.4, 3.4 shift inverse, and that gives me 0.29. Okay, so that's 0.29, and we'll make everybody happy by putting the little 4 in there. Okay. Once again, we're dealing with a single 1 in the numerator because this is outside the physical lens, right? So we don't have to worry about what the lens is made of. We're assuming that it's air out here, so we're just having our standard 1. So take the inverse, 3.4. That's going to be in front of the lens. So that's going to be in a negative space or in front, or you can just have your negative over here. That gives you the negative value here. So that is point from this position here. So the image that's given to you here, I'm going to say the image, this is our image, I'm drawing a dotted line here, is going to be 0.294 from the primary Gaussian plane over here. All right. If you wanted to know where that was from the actual front of the lens, I'd take the 0.294, all right, and I would have to add in the 0.028. That's the distance between the front of the real lens and the front of the Gaussian lens. And I add those two guys together. That gives me a 2. That also gives me a 2, and that gives me a 3. Right. Does that make any sense? Yep, that makes sense, I guess. 2.94. Yep, and then I'm going to add my 0.028. That gives me a 12. That's a 10. That's a 12, and that's a 3. Yep. And so the distance between here and here is going to be 0.322. So depending on how the answers for the questions are going to run, if they wanted to know if it was from the Gaussian plane or from the real plane, these would be your two associated answers. And then if you need a sign associated with it, once again, it's going to be this, and that's a minus, and that's a plus, and that's how those two guys add together. All right, so easy enough. All right, so once again, U plus D equals V. These are all Vergence values. Vergence in, power of the system, Vergence out. Okay, and so this is the reason why we're doing Gaussian optics, because it makes your world easier. All right, the problem also asked you wanted to know the image size. Okay, so then once again, magnification, our magnification factor, is going to be the ratio of the Vergence in over the Vergence out. Okay. And so the Vergence into our system is going to be what we have here. That's going to be our minus 8.2. Okay. And then the Vergence out is what we got over here. That's our 3.4. And then once again, both, so I have a negative Vergence in, I have a divergent wavefront coming in, and I have a divergent wavefront coming out. So I have a minus over a minus. That gives me a plus. And then I'm just going to give you this number here, right? This number is bigger than this number, so what does that mean? That means our image is going to be larger than the object, right? So that's 8.2 divided by 3.4, and that gives me 2.41, let's say. So 2.41, this is diopters, and that's where the X power comes from. It's a factor, okay? And so the magnification for this system is going to be 2.41x. The positive means that that image should be upright, okay? And it should mean that this image should be approximately 2.4 times the size of the image over here. All right. Now, when you look at the little picture that was given to you on the problem, they told you that this object was 4 centimeters tall, 0.04 centimeters tall this way. All right, so if you wanted to know the actual size of the object, you would take the 0.04, that's the size of the object, times your factor, which is 2.41, and that gives you the size of the image, and that guy is going to be 0.04 times 2.41, and that gives you a little more, not quite 10 centimeters tall, and let's make it 10 centimeters. It's 0.964. I'm just going to make it 10 centimeters approximately, all right? Which means that this guy over here, from here to here, he is actually 10 centimeters tall. All right, so depending on how the answers for the questions run out, you can answer a number of different things. All right, so that was for our meniscus lens that has a positive front base curvature and a negative back base curvature. Number 2, we're dealing with our biconvex lens, and I'll switch papers and then we'll work on that one. All right, so we're going to start our second problem. Okay, this is from the problem set. We're now doing the second problem here. All right, and so in the second problem, you're dealing with a biconvex lens. All right, so you have a positive front base curvature, and you also have a positive back base curvature. All right, so this is how they made spectacles back in Ben Franklin's day, and we're going to see how these things work out. All right, and so once again, we're going to assume that light is traveling in this direction. All right, and in the problem, you are given that the front base curvature is a +4 and that the back base curvature is a +2.55. So we're going to add another 0 over here. Well, that's kind of an odd number, 255. Why do you think they made it that way? Well, we'll figure that out in a second. The thickness of the lens stays the same, all right? So that's not a variable for this problem. Both the original meniscus lens and this biconvex lens is 10 centimeters, and it's also made out of the same stuff. So we're going to say the N2 is 1.5, and then we're going to do our calculations again. Once again, you're going to find the system powers, find their focal lengths, find the principal planes, and then they're going to ask you some questions how it changes from one to the other. Okay, all right, so we're going to figure out what our equivalent power for this system is, and that's going to be a combination of the power of the front surface or the front base curvature plus the power of the back surface or the back base curvature minus this compensation factor, or our thickness and the front power and the back power. And so in this case, the front power is going to be our +4. That's going to be plus our back power, which is a 255. And then once again, our thickness is going to be the 10 centimeters. But once again, don't forget about that is made out of something. In this case, that is a 1.5 index times the front power times the back power, which is our 255. And if you do the math for that guy, this guy comes out to be about 587. So an overall plus lens. All right, and so once again, back in the old days, you would take the 4 and add it to the 255. That would be a 655, and that ain't 65, and that's because this thing actually has thickness. All right, so once again, we have left Kansas. All right, so then we're going to figure out what the front vertex power is, and the front vertex power is going to have something to do with the equivalent power and the ratio of our thickness. Once again, front vertex power, light hits the back first, okay? And so the equivalent power, you just figured out what it was here. That's your 587. 1 minus, this is going to be the same thickness, the same index of refraction, and the power of the back given to you in the problem was your 255. Okay, and so do the math on that guy, and that guy's going to come out to be a positive 707. All right, so that's front vertex power. That's you reading that with the temples facing you. All right, so not the way that normally people wear glasses. We're also going to figure out what the back vertex power. The back vertex power, once again, is going to be dependent upon the equivalent power minus the thickness, 1 minus the thickness. Back vertex power, the power enters the front of the lens first, so that's the power of the front. All right, and so that's going to be what you calculated before, which is your 587, 1 minus 10 centimeter, thickness divided by the index of refraction, and then the power of the front given to you in the problem is a positive 4. All right, crank the math out on that, and that comes out to be 8 diopters. So 8 diopters is how it would read temples away, okay, reading it in a photometer, or how people normally wear their glasses. And you'll notice that in our first problem, the front vertex, or the back vertex power was also +8. And I want to make sure I'm not lying to you here. Let's see what I did with the math from the original problem, which was over here, and we found out. Here's the problem before, right? This had the positive front and a negative back base curvature. And look at that. The back vertex power is a +8. The back vertex power is a +8. That means if you took these two glasses, which look completely different, the lenses are shaped completely different, and read them both in a lensometer, a photometer, they would read the same. But it's obvious, as we're working through is these two glasses will not perform in the same manner. Okay. All right. So we figured out what our powers were: our front vertex power, our back vertex power, our equivalent power, and then I want to figure out what the associated focal lengths are for those fellows. Okay. So I want to know what the focal length is for the front vertex power. Okay, and that's going to be the inverse of our front vertex power. The focal length of the front vertex power is going to be the inverse of the front vertex power itself. Okay, and so that's going to be 1 over our 707. Our numerator is a 1 because the focal lengths are going to be out here or out here, not in the lens but outside the lens. And once again, unless we're told otherwise, we're assuming that this patient is wearing these glasses in air and not in a swimming pool. Okay, so take the inverse of your 707 and that gives you a 0.141. But once again, this is front vertex power, so it's going to be in the front, so it's going to have a negative sign associated with it, all right, which means it's going to be over on this side in front of the lens. I'm going to figure out where the focal point of the back vertex power is. That's going to be the inverse of my back vertex power. Okay, and the back vertex power we calculated here, and that's going to be 1 over the 8, and that gives me our 125 that we figured out before. All right, but once again, that is going to be on this side. So between the lens and the eye, that's going to be a positive direction. So that's a plus 0.125. All right, I need to find out where my equivalent length is going to be. So the focal distance of my equivalent power is going to be nothing more than the inverse of the equivalent power. All right, and the equivalent power, you figured out what it was over here. That was your 587. Once again, that's going to be outside the domain of the lens, so it's also going to be air. That's where our numerator 1 comes from. Take the inverse of that, and that's going to come out to be 0.170. And so that could be in front of the lens, which we're going to say a minus in front of the lens, but there's also going to be a secondary Gaussian focal point, which is going to be behind the lens. So it's going to be the same numerical value, but the sign is going to be different, okay? Because once again, our equivalent power that we're going to have has no thickness. It's an SSRS, which means that the focal distances are equivalent front to back. All right, and that's what we got here. And that's the reason why we're doing this. It makes our life so much easier. Okay. Now I need to find out where these Gaussian planes are relative to the real planes. All right, so where the fake lens is relative to the real lens. All right, so we're going to determine our E, which is going to be the physical location of our primary Gaussian plane, okay, and that's going to be the difference between the focal point of our front vertex and the focal point of our equivalent power. All right, now we're also going to find, well, we'll get to that. All right, so we'll do the math on that, and so this guy, you just figured out what it was over here, so this is our minus 0.141, and I'm going to subtract from that our distance over here, which is going to be our minus 0.170. And once again, we're doing a minus time, minusing a minus, which gives us a plus. This guy is bigger than, actually this guy is bigger than this guy, so we're going to end up with a positive value when we do that. Excuse me, and that's going to be a 0.029 difference between the two, and that's going to be a plus value here. I'm going to figure out where the location of my secondary Gaussian plane is relative to the back of my real lens, and that's going to be the focal distance of the back vertex power minus the focal distance of the back equivalent power. All right, and so the the focal distance of the back vertex power, you found out over here, this was a plus 0.125, and I'm going to subtract from that our fellow over here, which is my 0.127, but that's also going to be a plus. So that's going to be a plus minus this value here. This guy's bigger than this one, and so in this case we're going to have a negative value. All right, so this is going to be a negative 0.045. So 4.5 centimeters here. All right, so what does this mean? Oh, this is kind of kooky. And so this one over here, different than what we had before. This guy over here, this means that the primary Gaussian plane, what I call the H1 plane, is going to be in front of the front lens. This one over here, this is going to be the position of the secondary Gaussian plane, or the H2. That's actually going to be behind. This one's going to be in front, so it's going to have a wacky kind of shape to it. Definitely different than our system that we had before. All right, so this guy is located to the left, whereas this guy is located to the right. All right, we're going to have to draw that fellow out and see how he comes. All right, and so let me draw some pictures and then we'll come back to that. Okay, so we're back on problem number 2. We determined what our powers are, and from that we determined where our focal points is, and now we need to draw a picture of where the Gaussian planes are relative to the actual planes. All right, so once again we're dealing with a biconvex lane, positive front and back base curvature. Okay, and so for the system it was given to you that I had a positive front and a positive back, and the front base curvature was given to you as a +4, and the back base curvature was given to you as the 255. Right, again, 255, it's a funky number. Why do you give you the 255? That's so the two base curvature, the back vertex powers of the two lenses worked out to be the same. All right, that was the whole trick of the problem. The distance between the two here is our thickness, which is our 10 centimeters, okay? And then we need to know where our H-planes are. And we found out that our E values, so my E, which is going to be the distance between the real lens and the Gaussian lens, was a +0.029, and our E prime, we calculated that before, that was going to be a -0.545. This is going to be the distance between the back of the real lens and the back of the Gaussian lens, all right? Which means that our primary Gaussian surface, or our H1 plane, is going to be on this side, +0.029. So the distance between here and here is going to be a 0.029, all right? Our H2, okay, which is going to be over here, that is going to be to the left, right? That's where the minus came from. So the distance between here and here is going to be the 0.045. All right. And so if you try to compare the two pictures of the one where we had the two lenses that have the front face curvature and the back face curvature over here. This is from problem 1, right? So here's the front power positive and the back power negative. You'll notice that the H planes, both of them, had shifted forward. Here's the back, so this is the front of the real, the back of the real. This is the front of the fake or Gaussian. This is the back of the face or Gaussian. So if you took that lens, both of them shifted this way. If you look at this biconvex lens, what happens is the fake front shifted this way and the fake back shifted this way. So the lens actually collapsed on itself. And if you think about it, that makes sense because these two things are both plus, all right? So they would shift in the same relative direction. In other words, the overall power of this system you would think would be halfway in between. And so the overall power is located somewhere in the middle. When you're dealing with a lens that looks like this, in this case, this was our first lens, which is the meniscus-shaped lens that looks like this. Where is the power here? And so this guy shifted forward, so its power is located more towards the front of the lens, or in this direction over here. All right? And so that is how you're going to draw your ray trace diagrams. Now, they don't want you to do a ray trace diagram for the second one. They're going to ask you a series of other questions. Which way did the principal plane shift as compared to problem 1? Well, we just said that. They actually shifted inwards rather than shifting both in the same direction. One, they shifted in opposite directions to the other. What is the significance of having the same back vertex power? Well, the back vertex power of this lens was a +8. The back vertex power of this lens was a +8, which means both of these pairs of glasses that look completely different, these spectacle lens, if you read them in a photometer, read exactly the same. But it's obvious that the lenses itself, the locations of the power of these lenses, this one once again is going to be somewhere in here, this one is going to be somewhere in here. The perception of the patient when they're actually looking through these two lenses are going to be completely different, okay? Although they will still read the 20/20 line if those glasses are for them, all right? But the perception, what's going to be going on in this person's brain and in this person's brain over here are going to be completely different. So perceptually, they will change things. Not only image size, we're talking about magnification, minification, but how the actual image of that object is going to appear on the back of the lens, although both of these will be at the plane of the retina in focus. And that's what you need to understand, because you may have a patient that comes in with a pair of glasses, sees 20/20, you write them a prescription based on what they're wearing now, but then when the optical actually makes the lenses, they may switch up the base curvatures on you. And depending on the power of the prescription, if the base curvatures are switched, the perception of the patient will be different, and they may like it or not like it depending on the perception of the patient once again. But when you actually go to read the lenses or the spectacle lenses in the photometer or your lensometer, they will read the same. All right, so once again, the only way for you to tell what the problem was is to use a lens clock to see what the curvatures are. Once again, one of those things you're not required to buy when you're here, but is probably a good tool for you to buy if you want to do this for a living. Okay, all right, so that's all we have to do for this week. Next week we're going to look at something more about the image sizes. If you have any questions on this stuff, we're not doing emails. You're going to post your questions to the discussion board. All right, see you next week.